Okay, so we got the clock tower. The minute hand is 4 feet long. The hour hand is 1.5 feet long. And we're representing the distance between the tips as the quantity C. What about the length of the minute hand? Is that a changing or a constant quantity? Constant. Does it ever change? Stays 4, right? And then the hour hand? Changing or constant? Constant. Okay, so we want to first just define a function that gives the distance between the tips of the hands x hours after 3 p.m. So just open it up for ideas. So here, I'm prompting you to the very thing I've been trying to train you to do, which is we want to build a function around the quantity that we're interested in. The quantity that we're interested in here is this distance between the tips of the hands. And so here I'm just explicitly asking you for that function. Normally you would have to think, oh, I want a function of, right? But here I'm just explicitly asking you for a function for C. Any ideas? Don't be shy. How are we going to come up with a function? First of all, it'll be a function of what? What input variable will we have that's changing that will result in different values of C? Time after 3 p.m., theta. Which do you think? So those are both, yeah, those are both changing quantities, time after 3 p.m. and theta, that will affect C. Which one is going to be most convenient or most easiest to work with? Yeah, probably time, right? So time after 3 p.m. is probably going to be, well, let's see if we can just come up with something. So those are both candidates, okay? So time and the angle are both candidates. We know that as the time changes and as the angle changes, this value C will change. So let's just keep open and see if we can just get something that relates this changing value C to something else. Any idea? No one's thinking the obvious here. There's kind of something obvious first reaction that you might have to this is what? A relationship of quantities that involves C. Okay, she said Pythagorean theorem. We got some of the other things for thinking that. What do we think about that? Does that work? What do you think, Ellie? Right, yeah, so in the picture, yeah. 3 o'clock, we got a right triangle, right? So C is definitely, the Pythagorean theorem is going to apply. Okay, but Lizzie, you're saying something different. At 3:01? What will be happening at 3:01? How about 3:05? Is that okay? At 3:05, is it a right triangle anymore? Yeah, in fact, that angle it's rarely a right triangle, right? It's rarely a right triangle. So what do we have that can give us this length C, no matter what the angle is, no matter what the time is? What's that? Cosine, okay. Well, just strictly cosine still depends on a right triangle, right? So we kind of need, so Pythagorean theorem is a good idea, because this is kind of like the long side of a triangle, but we need an adjusted version of the Pythagorean theorem that will work for angles also other than right angles. Anybody know what that is? Pre-calculus? One person? An adjusted version of the Pythagorean theorem? Yeah, David.
Can't use the right triangles to
Okay, possibly. Trying to think. Yeah, it gets a little tricky because the orientation of the hands is changing, like in terms of where that altitude would be. But I think that this variation of the Pythagorean theorem kind of takes that into account and does that all for you. Does anybody know what this is? What formula this is? It's like a Pythagorean theorem that works on any triangle. Really, no one? Okay. It's the law of cosines. Okay, does anyone remember the law of cosines? Remember it? Okay, so it's as soon as I start writing it, then you'll be like, oh, you're right. It's just like the Pythagorean theorem. But then there's an added term that takes into account if the angle is not a right angle. And that added term is this, minus 2ab cosine theta. So whoever said cosine theta was on the right track. It definitely has to do with cosine theta. But so this is basically a version of the Pythagorean theorem that works for all triangles. And you have this adjusting term that adjusts for when the angle is not a right angle. And when the angle is a right angle, what is the cosine of theta? In other words, remember on our circle yesterday? When you have a right angle, 90 degrees or pi over 2, what is the cosine or the x-coordinate up at the top of the circle? 0, right? And so you get the Pythagorean theorem in the case where you have a right angle. This thing is 0, and you're left with the Pythagorean theorem. Any other angle, you have this adjustment. If it's an acute angle, it's going to be shorter, and so you're going to have to actually subtract. If you have an obtuse angle, that opposite, the hypotenuse, quote-unquote hypotenuse, will be longer, and cosine's negative, and so you'll be adding on. Okay, so we got the law of cosines, and so this is going to give us that length c in terms of time or theta. So we want c, so this is going to very conveniently give us c as a function of what? Theta, right? So write c as a function of theta. So we can do it now. So write what will the length of the distance between the tips, what will it be at any time, or for any angle between those things? Okay, Kyle, did you get it? Did not get it? How about Trevor, you get it? Okay, so is there anything that we know in all that stuff? I like that, square root of. Do we know any of that stuff? Yeah, Lizzie, what? 4 squared. So A and B are just the lengths of the legs, right? Just like Pythagorean theorem. So 4 squared plus 1.5 squared minus, and let's so go ahead and simplify that while I'm working to write this down. I believe you. Just give me a second. Tell me again, Tony. 18.25. Someone else agree with that? Okay, so good start. Now the question is, what does A ask for? Did we achieve what A is asking for? Or not? What's that? Do we have an input for, do we have a value for theta? Why not? Reshma, why don't we have a particular angle for theta that we're going to plug into this? Yeah, it's constantly, so it's the idea of a function. You got, theta can take on many, many values, and so we express it as a function. Theta can take on all these different values, and then for each one it takes on, the function cranks out the distance between the tips, right? That's the idea of function, right? A set of input, each input pointing at a certain output. Okay, let's write it again up here. So what do we need? What's lacking here? So we got C of theta, 18.25. What was this again? Okay, do I have it right? Okay. Why is this not the function being asked for? Yeah, Dave.
It's asking for the function in terms of x hours.
In terms of x hours. So the next thing we have to do is very similar to what we've been doing with all these optimization problems, right? We've got a function in terms of one or more variables, and then we have to change that input. How are we going to do this? So what, in general, how are we going to get? We want C of what? X. So what's our strategy for getting C of x, where x is the number of hours after 3? So I'm not asking you to tell me the answer. I'm just saying, what's it going to look like getting this C of x function? How are we going to do that? Just in very general terms. Jason? What's that process going to look like? What's our goal in order to write this as C of x? No idea. Ben, you've done almost every optimization problem so far. Ben, any idea? Just in general, what's this process going to look like to get C of x from C of theta? Right, any idea? Theta in terms of x, exactly. We need to get theta, so we need to get the angle in terms of time. So we want to know so for a certain number of hours after 3, we need a rule that tells us what the angle will be. We're going to do that. So we need theta equals something with x's. Some rule where we can express theta in terms of the time that's gone by after 3 o'clock. Yeah, Lizzie. 2 pi x. Okay. Okay, but yeah, but both those are turning, right? But both the minute and the hour hand are turning. Yeah, David. Okay, so what arc length is it? Okay, let me pause it. So you want me to draw the hour hand? Like that? Okay. Okay, so you're saying starting from 3, there's some distance that this moved, and then there's some distance that this moved, distance of the hour hand. Okay, and theta is what? Well, what did the distance start at? Yeah, pi over 2, right? So it started at pi over 2, and we added that distance, but we also subtracted that distance, right? And so this is theta. So if we could get these distances in terms of x, so what's the distance? Nice. Okay, so what's the distance that the hour hand moves in x hours? How far does the hour hand move in x hours? It can move in hours. So how far at distance? 1/12 of the whole circle. So 1/12, and what's the whole circle? 2 pi, and what's r? 4. Now that's in 1 hour, right? So 1/12 of the circumference. That's how far the hour hand moves. That's in 1 hour, so how about in 2 hours? 2 times that. How about in a half hour? Half of that. So how far does it move in x hours if it moves this far in 1 hour? What's that? Yeah, so just times x, right? Okay, so did I lose anybody? So do you see where we got the pi over 2 plus dh minus dm? Does that make sense? Well, this is a really good idea that David had. The distance between those is basically 4 theta. Okay, the distance between. So this is really the distance. Really is 4 times pi over 2. But we're just we're just doing the angle, right? So yeah, that's right. Okay, so pi over 2. But this is just the angle. So Okay, so we want to do arc length. All right, so S equals 4 theta. That's what we're talking about here. So the distance, so we're kind of crossing. We got a radius 4, so we're kind of crossing theta and S. We want to get that straight. So let's write what 4 theta is, which is, then we can talk totally in terms of arc length. Okay, which is always 4 times theta. So this is our arc length. It's always, because the radius is 4, it's always 4 times theta. So we have 4 times the initial angle, pi over 2, plus the angle covered in x hours by the hour hand, which will be 1/12 of 2 pi x. What about the distance that the minute hand covers in 1 hour? Yeah, the angle, it makes 1 full rotation every hour. That's right. So then in x hours, it'll be 2 pi x. Okay, so we got theta in terms of x. So theta is just simply then this thing in parentheses. So we did this 4 theta because we wanted to talk about it in terms of arc length, the way David suggested. But theta then is just the initial angle, pi over 2, plus what the hour hand will move every hour times the number of hours, but then minus what the minute hand will move every hour times the number of hours. So we got it. So theta then is that thing right there. But I think this can simplify, right? So how does that simplify to? What does that simplify to? So now we got C of x. 18.25 minus 12 times cosine of pi over 2 minus 2 pi over 12 minus 2 pi. That negative 11 pi over 12? Check my math. 2 pi over 12 is pi over 6 minus, minus this is that 12 pi over 6. So 10 minus 10 pi over 6. Any help from the crowd? 1/6 minus 2, which is 12/6, equals negative 11/6. So we got theta in terms of x. And so now we've got c in terms of x because we can just plug that theta in. All right, so ask the questions. Where did I lose you? I'm sure I've lost at least some of you somewhere. So let's talk about it, make sure you understand it. Did you see the approach though?
Yeah.
So we just looked at, let's figure out what after a certain amount of time, what is this distance from here to here? So we know it started at pi over 2. And we added this much to that distance, and we took away this much from that distance, right? So that's that first thing. And then, so what is that angle right there? Well, it's how fast in radians per hour it's traveling times the number of radians, times the number of hours. So radians per hour of the hour hand is 2 pi over 12 radians per hour. So it goes 1/12 of 2 pi per hour. So we got the number of radians per hour times the number of hours. This angle, that's this theta m, this theta h. So this goes 2 pi radians per hour times the number of hours. That's how that angle changes. Does that help a little bit? Okay. That's all we have for. So, yeah. Challenging problem. Okay, I got office hours for the next hour if you got questions on these problems. So, the ones that are due tomorrow or Friday.